And here we are again, folks, talking more about radiation. So, welcome to the new age. We're going to deal with beta. Beta radioactivity, naturally occurring. Um, well, remember, there's three types of naturally occurring radiation: alpha, beta, and gamma. From the last video, alpha is when the strong force doesn't extend far enough to hold a nucleus together, so a chunk of it literally breaks off and goes flying. This is now beta. Beta is when a neutron changes its mind. It literally becomes a proton. In the process of becoming a proton, it spits out an electron. All right, that's beta decay. What's even stranger about that is just because a neutron becomes a proton and electron doesn't mean that a neutron is made up of a proton and electron. I mean, why would anybody think that? Good Lord. What is happening is a much more fundamental particle is involved, but protons and neutrons are made up of things called quarks, specifically three quarks. There are up, down, strange, charm, and top, bottom type quarks. You'll learn about those later on in a different physics class, but quarks are what come together in this example to make protons and neutrons. Well, a neutron is made up of three quarks: an up, a down, and a down. Fine. A proton is made up of three quarks also: an up, and a down. And so all those three quarks are three little guys dancing around very close to each other in a region of space that they don't escape from. So that region of space we call protons and neutrons. Well, on a fundamental level, on a quantum level, one of those down quarks changes its mind to become an up quark. That process is mediated by what's called the weak force. All right, remember we had a strong force holding atoms together on a larger scale, on a smaller scale holding nuclei together on a larger scale, on a smaller scale holding a neutron together, or the quarks that are involved in a neutron, is something called a Z boson, a Z particle, or weak interaction. All right, so the weak force is what is in control here. Which again, when you take a more advanced physics class, you'll learn more about. But quarks can change their mind. They can change how they express themselves, and there are things that mediate what quarks do. Those mediators are called bosons. This one happens to be what's called a Z boson, and it is a mediator of what's called the weak force. Remember, there's four forces in nature. That's why they're called forces. Two of them only exist inside the nuclei of atoms. The weak one, which is what we're dealing with in beta decay. So I want you to associate those two together. Beta decay is associated with Z and weak interactions, okay? Like then the strong force is associated with alpha decay, all right? And the carrier for that, I didn't tell you in the last video, the weak force is carried by a Z boson. It's called the strong force, acts like a very strong glue to hold protons together. So that's called a gluon. The carry, then there's the electromagnetic force, which you all know is a photon. And gravity is carried by something called graviton. So just a bit of a introduction to particle physics for you there. All right, but remember, it's what a beta decay is a neutron becoming a proton through a weak interaction where a down becomes an up. It looks like this. A neutron becomes a proton, spits out an electron, which we'll call a beta particle, gives it kinetic energy the same way an alpha particle did. And this is where we're also introduce you to something called a neutrino. All right, but remember that N, remember the subscripts down there. We've been calling that the atomic number, the Z number. Well, if you're a neutron, you don't have an atomic number because you don't have any protons. So your atomic number, your Z, would be 0, wouldn't it? So its Z is 0. You can also think about it as the charge of that object. What's the charge of a neutron? 0. And the number up top, remember, is the mass. So the mass of a neutron we're going to call 1. It becomes this item, a proton, which makes sense that its subscript is 1 because it's the atomic number of a proton is a, and how positive is a proton? It's positive a, and it's got a mass of 1. Now over here, this beta particle, that's what it spits out. That's what goes flying into the atmosphere. Since the mass of a neutron and a proton are essentially the same, we're going to call this a mass of 0, even though it's not 0, okay? That 0 is an ish. We will call it a -1 charge, though, because it's got a charge in -1. So the particle that goes flying is very small mass, has a charge in -1. Well, my gosh, that's an electron, and that's what I want you to remember a beta particle is an electron, okay? So it's weird. It's an electron, comes flying out of the nucleus, because electrons don't hang out in the nucleus. That's why it's weird. But again, the electron wasn't there. Okay, it's not hanging out. It's not like a neutron is made up of a proton and an electron. It isn't. The electron was expressed during the interaction of the quark changing its structure, and it spits out matter when it does that. It gives it kinetic energy because that electron has to move. So there's some kinetic energy given to it. And then this is something you haven't seen before. It's called a neutrino with a bar over top of it. It's called an antineutrino. That is actually an interesting story for you to follow if you want to look it up. But neutrinos were discovered on chalkboards really before they were discovered in particle accelerators and particle detectors, because the energy and momentum of these particles as they're flying apart, they weren't quite adding up. It seemed like something was missing. We can't account for a certain amount of energy and momentum. And so they coined the term, there must be some very small neutral object, neutrino, that they were looking for, and sure enough found it. I wouldn't be telling you about it. So that's the reaction. So remember, those subscripts can be thought of as two things: the atomic number or the charge of the particles involved. Okay, so this example is what we left our alpha decay example with. The daughter for that alpha decay from the previous video was this thorium-234. I think it said that thorium-234 decays by beta. So that's what we're going to start with. It's got a 90 atomic number, thorium-234. Now remember, what happens in beta decay is one of those 234 neutrons becomes a proton. So that 90 must become a 91, which means we need to know what element is 1 higher on the periodic table, which, we can get by looking at this. So the thorium, which was 90, becomes Pa protactinium 91. That's how we figure out what element goes there. So that's a 91. I'm going to write Pa, the state of Pennsylvania. The mass, though, didn't change, right? Remember, a neutron and a proton are essentially the same mass. So this is going to stay 234. All right? Now, remember what went flying through the atmosphere was the beta particle. That beta particle is written as the letter E. It's an electron. The charge of an electron, you know, is -1, so that goes down there. And again, I said the mass is ish. We're going to ish that mass to be 0 for this particular example. All right? And then we said there's also some kinetic energy given to that electron as it goes flying through the air. And we have the antineutrino, which the V sometimes is written as a cursive letter N, but that's the lowercase Greek letter N. So the parent becomes the daughter. This is what gets spit out in the environment, and it's got some kinetic energy in that, okay? The energy involved with this guy, we will calculate the same way we calculated it before. We're going to take the mass of that thorium-234. The more Pacific mass of it is 234.04361. the mass of this protactinium-234, you would look up on that same data table, and it's close. It's 234.04330. All right, so the differences in mass in beta decay is always going to be less than the differences in mass in alpha decay, because it's just a proton and a neutron trading places. So that difference in mass is very, very, very small. If you push the minus button between these two guys, you will get the number 0.00031 U's. So there's the atomic mass difference in those twos, which you then multiply by that conversion that I gave you before, 931.5 MeV, mega electron volts, and the energy associated with this in mega electron volts becomes 0.2887. There's a bunch of other digits, MeVs. Now, that decimal is an awkward way to say it. In other words, we would use mega electron volts to call it that. We will move the decimal point 3 spots over and call it 288 or 289, 288.7, maybe 289. It depends how precise you want to get, but then that's thousands of electron volts. All right, so 289,000 EVs. Now, this again is electrons being spit out into the environment. And so, is it ionizing radiation? Yes, it will ionize because it's dumping electrons into the environment. So, if it ends up anywhere near you, it's shoving electrons inside you, and it will change the chemistry of your body tissues. All right, and is the daughter stable? And probably not. We will look up the decay chain of what this is called when we do this by the same things I showed you before. But this is the thorium. And if you look on the left there, 234, its half-life is 24.074 days. So 24 days is a half-life, which we'll learn more about. Look down at the bottom, just below that, high decay modes, probability mode. Beta is how it decays. Next to that, 273 kiloelectron volts. Its daughter is 234 protactinium, which I will show you right there. This is protactinium's 234, so apparently it is not stable. Its half-life is 6.66667 days. So protactinium 234 is not stable. It will decay by beta also, which means it will climb back up to become uranium 234. Again, its atomic weight is over there. So this, again, protactinium 234 decays by beta. Its half-life is only 6 days. So there's that. The thorium, again, number 273 kiloelectron volts is what I calculated is 289. They were calling it 273. It's just differences in rounding, I'm sure. Stable daughter, in this case, no. It continues to decay. To decay. And that's what these decay, chain is being shown for you here. I'll scroll down, and I know it's hard to read all of these, but that decay chain on the left there has the patterns, the elements, the atoms that those different decays turn into, and most of those decay chains end up with some isotope of lead. It'll end up as what I call peanut butter. But if it ends up as lead in that decay chain, that's usually when it is done. It's done decaying. It becomes stable. Not all decay chains end in that, but these particular ones do. And again, it could also give off gamma. Remember, same as what we said before. If it's giving off gamma at the same time, then you would be scared of it. These electrons can go a little farther than alpha particles can, but they still have an same ionizing effect. You can block electrons with just a piece of cardboard or something, but you can't block those gamma rays, all right? If it gives off gamma when it's excited, the nucleus could give off gamma. So anyway, 15 minutes Aloha.